This is lecture number 9, E512, analog IC design, and today is September 15. Yeah. So now let's go to the next, topology, which is source degeneration. It is similar to what we have as what is the name in BJT when you are similar name of source degeneration. Huh? Emitter degeneration, right? So what you are doing in source degeneration or emitter degeneration? We'll keep the one resistance over here, right? Right at the source. Right? So with different loads, whichever you like, you can keep it. So what could be the advantage of source degeneration? Yeah. So how did you get that linearity?
So, with that voltage difference,
Hmm? Which voltage difference?
this ID into RS.
ID into RS. Okay. ID into RS. That voltage will become what? How it's linear?
So RS voltage is stable by its own.
You were saying something in right direction. What you were saying?
So there is a voltage difference.
ID is actually ID. You know that it's a non-linear current. How do you make that current linear? Okay, so I would recommend you just look at the common degeneration. So he's right. It gives the linearity. Better, SNR, better things will be there, right? So that's the advantage of source degeneration. I'm not going into much into detail, right? So I'll solve this. I would recommend you just go through my another course on analog circuit design where I explain this in terms of emitter degeneration. So same answer is for source degeneration also. Okay, so let's not repeat that. Okay, so if this is the case, let's now find out the gain when you have this situation with the resistive load. Right? The resistive load RD is a load over here. So what will be the gain? If you are looking from this side, what are you going to see?
RS in series with 1 by GM parallel 1 by.
Yeah. So RS in series with 1 by GM, right? If you want to add other things, you can add others. If it is body effect and all. If it is not there, it's like this, with minus sign, and looking from upside, it's RD in shunt with RO1. Okay, so that's the resistive load. I believe there is no problem in this, right? It's very simple. Now let's assume this is already we know about it, right? So this is just a revision of what we have done. If you are looking from this side, it's 1 by GM. Uh, from here, it's R0. Looking from any side of this kind of diode connected load, it's 1 by GM. Looking from this current as a load, this is current. What's your name?
Vishal.
Vishal. So this is as a current. Looking from drain side, it's RO, right? So these are the just revision what we did, and we will use it over here. So now various loads are given, and various topologies are there. Already we know all these answers, right? Already you solved this as a part of surprise quiz. This also we solved. Okay, now okay, anything else which is left? Okay. I'll make maybe few more question over here. Now tell me, what is the gain? Hmm?
Same.
What same?
Last
No, why same? Why same?
one. Equivalent to R0 or R0.
So you have to tell that, right? Earlier it was RD, right? Answer was RD. Now it's not RD. Okay, let's try this one then. Now tell me. Tell me quickly. It's not easy, not difficult, right? Yeah.
R03 plus 1 by GM2.
What is it? Okay. R not 3 plus 1 by GM2. Okay.
Absolute part.
Right. It's easier, right? You can add other body effect and whatever you want to keep. Note that in this particular question, when it is not written, it obvious that it's a body effect will be there. Okay. So if you want to assume it, you should assume this under body effect. The reason is the entire book or whichever book you are following, when these connections are not shown, then NMOS is connected to NMOS body is connected to ground and PMOS body is connected to VDD. So this is by default. So if this is connected to ground, so VBS is not zero, right? But these two are. Then you should consider, right? So when to apply body effect, you need to say that. If this is not the answer, then you should say that then this is tied with source. Okay? Then you have to assume it or you have to tell that, right? But if it is not shown explicitly, then body is connected to ground and body of PMOS connected to VDD. So that is what you need to assume. Okay. So now let's make the schematic diagram of a common gate amplifier in your notebook with some resistive load maybe. You got it or not? You can. So common gate amplifier looks like as follows. So if this is the case, sorry, I made a mistake over here. V in is over here, and there has to be some V bias, right? Just to make sure that the transistor is in, you know, the saturation. So tell me the gain. In same direction, you need to find out the value of impedances, divide it, get the answer. Note that this particular situation is the situation when source and body are never tied together. As I explained, they are actually connected to ground or VDD wherever you keep it. So the answer requires to add body effect in common gate amplifier.
positive GM around?
maybe, but that's not the complete one, right? That's not the complete answer. Body effect is there. I'm saying body effect is there. You got the answer? Right. Generally, this is eta times GM, so you can write down eta RD times GM. By the way, you got positive. The reason is you are actually applying the voltage from here only. Not only because of that Thevenin equivalent, but you are applying that VGS. Look at this. Actually, source is having, you know, relatively positive. So in that case, the current has to be in opposite direction. The GM VGS should not be going towards source, but it should, away from source, right? So that's why that is what you should see like this. So this has to be like this. Right? Then it's easier. We know that looking from uh, source side, we are going to see 1 by GM in shunt with 1 by GMB, and other side is actually RO in shunt with RD, and it's positive. And accordingly, you can keep the values. So these are the things. Am I going fast or now you are able to understand? Okay. Now, some of the common gate amplifier remarks. The small signal gain of an amplifier is positive. Understand. Similar gain of the common source, however, the sign are different. Right? It's in phase output. If you are applying whatever you are applying, maybe with some delay, it's available, but ideally it's in phase, right? Whereas common source amplifier is having 180-degree phase shifted output, and both the amplifiers are different. Common source amplifier is the one whose input impedance is actually infinity, and output impedance is also infinity. So it makes this one as voltage controlled current source, or an OTA, operational transconductance amplifier, when we are going to make it with common source. Common gate amplifier is the one whose input impedance is what? And what is output impedance? What was the input impedance looking from source side? 1 by GM, so it makes it low or 0. And output impedance looking from drain side, it's R0, so it's high enough. So what we call this one? Right? No, it's current control. Current control, right? So it's a current. It's a current amplifier. It's a current amplifier. Whereas this is transconductance amplifier. Now let's go to the next one, which is also one of the popular one. Common drain amplifier looks like this one, whose another name is source follower, or also the voltage follower. Why do we call this one as source follower or voltage follower? Vivek? Not gate. Oh, sorry. Yeah, gate. So same is available at output. So input and output are same. Ideally, in phase, everything is same. So then why we are using such kind of amplifier? Hmm? Okay. So what buffer does? No, when to use such kind of configuration? Let's say this is you are saying. Hmm? impedance matching. Okay, impedance matching is a different thing. I would say impedance matching is altogether a big topic where you are matching the both the impedances same to have the maximum power transfer. In this case, it is one part is also there, but it may does impedance matching, but actually it makes sure that the loading does not happen. So it prevents loading. Loading effect is the one where you are losing the voltage, right? You wanted to have, let's say, I'll give you one example. This is the tried and tested experiment in laboratory of IIT Mandi. When I was teaching applied electronics, I was giving this. So if this is inductor and capacitor, just give me 1 minute so that I can find out the exact values. Okay, so if I'm going to do this one in the laboratory, and if I apply 1 volt, 1 kilohertz sine wave, it should work, right? There is no problem. Look, I'm not looking at output. I'm not interested in output. But at the same time, I want to see here this one. So what I'm going to see on oscilloscope, in your opinion? Look, I applied 1 volt, 1 kilohertz sine wave from the function generator. Look, I'm looking at just input. If there is blue correction, no problem, right? Let's assume that if this is not there, I'm going to see 1 volt, 1 kilohertz, right? Sine wave, no problem, right? So if this is the case, what's going to happen? Should I see 1 volt, 1 kilohertz in the oscilloscope? And if I'm asking this question, then you should not see, right? But why you should not see 1 volt, 1 kilohertz? What are you going to see? If there is any assumption, you can tell me.
It's a damping.
Hmm?
Some damping is there with the oscillator.
Where is the oscillator?
LC.
LC does not mean oscillator, right? I would say, look, if there is some pendulum, it requires somebody to give some push, then it will oscillate. Who is pushing it? Nobody, right? It requires to follow the Barkhausen criteria to make it oscillate. It will not oscillate. Okay, it requires more than one gain and phase also more than much more than 180 degree. There is nothing is fulfilled here. Okay, so that situation is not here. So tell me, understand? I am not seeing the output over here. Even if it is an oscillator, let's assume that this is an oscillator, then also it will not give you anything. Look, I'm expecting input only. Why oscillating and all? 1 volt function generator should show me the same thing. This is what we studied, right? It is a short circuit, understand? 1 volt, 1 kilohertz. So what we are going to see in oscilloscope?
The same thing, sir.
Okay, let's go this way. What is the input impedance of this oscilloscope? Mega ohm. Okay. I'm talking about our laboratory. Those like you people have worked in our laboratory. And you people are going to become TA or doing TA. So Please look at all these numbers. These are the numbers are already there. So I'm writing referring to our laboratory, applied electronics laboratory, or maybe control laboratory or communication laboratory. So all places same instruments are there, and this is the impedance. So around 1 mega ohm impedance for uh, Tektronix oscilloscope which we have. Okay, what is the output impedance of this function generator, or what do you prefer to have it? If it is high, then let's go this way. If output impedance is high, then the output is current or voltage? No, it's current. It's current, right? So then you can't see the current. Sorry, you can't see the full voltage over there. Okay, it's not possible. So if it is infinite, it's no good. But input impedance is infinite, then it's voltage, right? So that is what you have found out here. If you want to see voltage over here, oscilloscope's input impedance has to be very high, right? An oscilloscope is not measuring current. For current, you need some separate setup. You need separate current probe, right? So those things are. I'm assuming it is not there. So if it is there, if you want to measure current, then it has to be input impedance has to be low. How much low? 50 ohm. Okay, we have to remember three genius who found out this, right, together. So 50 ohm, 50, right? If it is not 50, generally when, okay, those people who are doing the TA shift understand if it will not be 50 ohm by default, then you will get sometimes wrong answer also. So your first thing is you should go inside the laboratory and you should set up the function generator at 50 ohm to get the correct answer. Some RF people, they do not rely on function generator. They actually terminate this input with 50 ohm. You must have studied somewhere, right? In communication that we are adding 150 ohm at the input side. So whatever the function generator is giving, it's all only seeing 50 ohm, right? So whatever the impedance is over here, 1 kilo, 2 kilo, 10 kilo, 1 mega. In any case, I'm going to see 50 ohm only. Okay, so 50 ohm. So if this side is 50 ohm, let's assume that it is something like this. So 1 volt sine with 1 kilohertz, right? This is what I'm seeing with 50 ohm, let's say here. Okay. This is inside function generator. And when I took the output, when I'm seeing an oscilloscope whose impedance is, let's say, wire will give you some resistance, let's call it 50 ohm. If here I'm looking into this is oscilloscope whose impedance you told just now 1 mega ohm, right? If it is 50 ohm, then in oscilloscope you should see 0.5 volt 1 kilohertz. Do you agree? If this 1 mega ohm is not 1 mega ohm but 50 ohm, then you will degrade the value of voltage, right? But the best case is that we are going to keep the 1 mega. So I should see near to 1 volt only with, without changing any frequency, right? This is happening because of the reason that input impedance is very high. If it is not, then it's bad oscilloscope. It will not give you the good answer, right? So, but what if I'm adding here like this? Now, how much value of voltage I am going to see over here? Now tell me. You all have done circuit theory, right? Network theory. You can keep it here. One more 50 ohm if you want, just to have. So looking into this, what is the resistance? Looking into this, what is the resistance? Okay, I made a mistake here. I should have kept even smaller, let's say, even if it is just I'm keeping some value, right? So with 1 kilohertz, I should see very small resistance over here, very small, less than 50 ohm, right? Much lower than 50 ohm. Then what will happen? I'll get much lower value than 1 volt. It is as good as 0. Same will be transferred over here at the oscilloscope, right? By the way, this is called loading effect because input impedance is low. It can take current, not voltage, right? I don't like this, so I can do either impedance matching or I can use something called voltage follower, right? So, right. By the way, uh, what kind of amplifier this one is? Voltage control voltage source, voltage control current source. Looking into input side, it's infinity. Looking into output side, what is the output impedance here? RS parallel RO1, right? RO1 itself is very high, right? So it's high, right? So, so that's I made some mistake or no, I made mistake. 1 by GM, right? 1 by GM, sorry. 1 by GM1, it is source terminal. So we are going to see 1 by GM. So it's going to give me low impedance. As the name suggests, at the over here, it's following the voltage. So input is voltage, output is voltage, and so voltage controlled voltage source, whose role is to just to make sure that both sides it's proper uh, proper impedances are there. So input side, when I took some voltage 1 volt 1 kilohertz from here, if I am going to drive a low impedance, I'm going to design this amplifier such a way that it can drive my whatever the impedance I'm keeping here, and accordingly I can look at the output. If it is required, I can keep one more over here also. So accordingly I can design. So this was one part. Sometimes this is very important in one of the very popular branch of study in VLSI known as the SIPI. Have you heard about SIPI? Many companies have one team who is working on this. It's called signal and power integrity. Some good companies like ST or TI and many other good companies, Intel, they have you know people who are working on signal and power integrity. They call it SIPI. So that's the name of the team generally. So they make sure that if the signal which we have given is actually reaching at the output efficiently, same way whatever power you are giving, it reaches very efficiently. Just if you want to see the example, what's going to happen? Look at this. If you want to, you know, I'm looking at this power integrity. Okay, signal integrity. Just now we have seen whatever we have seen was signal integrity. Power wise, understand. Let's assume that this red box is actually a chip. I'm not going into pad and other things, but if this is the circuit where VDD is connected, where I'm connecting, you might see that if you are going to use 1 billion transistor in your chip, almost like half of the transistor of that will be PMOS, right? And half of them might be NMOS. So half of the transistor will be connected to VDD and half of the transistor will be connected to ground. So if this is the case, we understand one thing. Looking into one side, it's 1 by GM, which is around, let's say, hundreds of ohm, right? If there are 100 branches are here, now the impedance looking into this must be less than 1 ohm if there are 100 branches. If there are 1000, 10,000, 1,000,000, that is the impedance this VDD will experience. So somebody has to design very efficient power supply which can drive not 50 ohm, but even micro ohm, you know. And in that case, it consumes lots of power. To have such a requirement, it requires lots of power and lots of things needs to be done. So that power integrity is really very important as we are moving forward in deep submicron technology, whose 1 by GM is also getting down, right? So this was just glimpse of what is going on. So accordingly you can choose. So this generally SIPI is not, their approach is actually analog or like RF people. However, they are dealing with the digital circuits. You know, they are looking into digital circuits which are going to give you signal and power integrity. So lots of problem like jitter and other things they are going to discuss. They are going to look at those things in that way so that they can, you know, test this circuit with efficient VDD. So we have to think about it, how to, you know, get rid of it. There might be lots of techniques you can use it. Anyway, so this is common drain amplifier, which is also source follower. Note that source is connected over here, and this is common drain because this is actually AC ground. Right? That's why it's common drain. Right? This is a drain terminal. Right? Okay. So now we need to find out the gain of this particular circuit. You can solve through equations also, but as I told you, for this one also, when you identify it's a common drain, you can go through some technique. The technique says that you can draw the small signal model like this, right? Okay, this is, I can draw maybe small signal. Am I making a mistake? No. Right? So it's similar to this one, what we have drawn over here. Just only thing is, okay, this might be a little bit difficult. Note that in this circuit, when it's a common drain amplifier or common gate amplifier, the input transistor has to experience the body effect. So in that case, you have to add GMB VBS. That has to be added, right? Right. So this is what you have to add. Let's assume that if you have here one current as load, then this is the circuit. Let's say when the current as a load. If you look at here, GMV1, that's the current from here. We replaced the body effect, that current source as 1 by GMB because that's a resistance with respect to ground. Whatever I have drawn, it is same thing, just a little difference that instead of this one, we remove this one and just we are keeping it with respect to 1 by GMB. Just for uniformity, I'm just removing this and also keeping here all resistances are down, right? And understand this is actually giving you two different sides of V out. One is actually driven by or driven by V in, which is a dependent current source, and rest of them are at other side. So you can see the voltage, voltage division between two resistances. One resistance is upside. So whatever you kept it over here, so that comes here. Let's call this one as R2, and this is 1 by GM. You applied here V in because of this one, and this is V out. So that's a voltage division between V in and V out with respect to two resistances. So when you are doing this, it's V out is nothing but R2 times V in divided by 1 by Gm plus R2, right? You can keep this V in this side just to get the gain. So if we know the R2, which is nothing but 1 by GMB in shunt with RO1, in shunt with RO2, in shunt with RM divided by 1 by GMB in shunt with RO1, in shunt with RO2, in shunt with RM. Right? That is going to give me the gain. So in common drain, the technique says that it's a voltage division between two resistors. One is clear cut, always 1 by GM with respect to rest of the effects. Just add that, you will get the answer. Same thing is written over here in this case also. If this is the case, it's 1 by GM1. Other sides are 1 by GMB1, RO1. Add all of them, you will get this answer. So it's a voltage division between this resistance and this resistance. So that is 1 by GM, and other side are other things, right? Same is true for the current as a load. By the way, are you following or am I going fast? What is the meaning? Yeah? Thoda fast. Okay. Maybe I'll discuss this tomorrow. Okay. So that with fresh mind. But are you following till now, right? No problem. Okay. So common drain amplifier is very popular and very important amplifier, or the very important invention, and it is used in many places. One of the places, the probe, where not MOSFET, but they're using JFETs, junction field effect transistor. If you use the probe, you will understand the tip is getting little bit, heated up because of that JFET. Junction is getting heated up. Like similar things they are using. It's actually a big branch of study, just studying probe. That's why they are selling at very high price. If you sell something like 10 to 5x probe, it should be almost like 30-35 lakhs voltage probe. However, if you are going into 10x or something like that current probe, it itself should be something like 2-3 lakhs. We have some probes available in my laboratory just below this particular place. Okay then, so that's all for today. Tomorrow we are meeting at 9:30. Okay.